The 3 most powerful laws in the universe. Hello everyone and welcome to my channel. The universe may seem chaotic, but there are 3 strongest laws in the universe. They are like the program code behind the universe, determining the rotation of galaxies, the birth of particles, and even our existence. Today, we will reveal the secrets of these 3 laws. 1. The law of vibration. Have you ever thought that everything around us, even the invisible things in the air, are in fact constantly vibrating? From macroscopic objects to microscopic particles, vibration is like the language of the universe. Through the vibration, everything between the establishment of some kind of connection, the formation of everything we see now. So, what is the law of vibration? Simply put, it means that everything in the universe, including objects, energy, thoughts, emotions, and even consciousness, vibrates at different frequencies. In fact, the law of vibration is not a new idea. Ancient wisdom has already realized that everything is not static, but full of energy and movement. For example, the qi in qigong is an invisible energy that is constantly flowing and vibrating. Indian yoga philosophy also mentions the sound symbol Om as the fundamental frequency of the universe. The law of vibration in Western science has been verified by physics in the 20th century, especially in the field of quantum mechanics, where the law of vibration has become an important basis for describing the material world. One of the basic concepts of the law of vibration is that everything is made of energy, and energy manifests itself in the form of vibration. You can think of this as meaning that all matter has a frequency, just like the sounds you hear, each of which has a specific frequency. Your favorite music is a vibration of a particular frequency, and every substance and phenomenon has its own frequency, and its vibration determines its characteristics and its way of being. Take a simple example. If you press a piano key, the piano strings will start to vibrate and produce the sound of a note. The height, quality, and clarity of the sound is determined by the frequency of the vibration of the strings. And the vibration of the piano string doesn't just happen physically, it also somehow interacts with the molecules in the air, transmitting the vibration to your ear, which then becomes a sound that you can perceive. The laws of vibration become even more mysterious and marvelous if we put our perspective into the microscopic quantum world. In quantum mechanics, particles are not fixed, unchanging point-like objects, but are in a constantly changing, constantly vibrating state. This vibration is called quantum oscillation. The existence of particles is no longer certain in classical physics, but a certain probability distribution. In other words, the position and momentum of the particles can only be determined at the moment of observation, and they are like waves that are constantly vibrating. In the famous double-slit experiment, for example, quantum particles, such as electrons, pass through 2 slits, and in the absence of observation, these particles vibrate as waves, exhibiting fluctuations. And once we try to measure their positions, they cease to be waves and become particles, displaying particle properties. This shows that at the quantum level, the way vibration exists is very flexible. It can be fluctuating, it can be particulate, and it can even exhibit both at the same time. In fact, scientists have discovered through experiments that the vibrational frequency of energy is the fundamental determinant of the alternation between fluctuation and particle in matter. In short, the vibrational frequency of energy directly affects the state of matter, and they interact in a certain way, thus constituting all the phenomena of the universe. In addition to microscopic particle vibrations, there are similar vibrational phenomena in the macroscopic universe. One of the most interesting phenomena is resonance. Resonance refers to the fact that when 2 objects vibrate at the same or close frequencies, a resonance effect occurs between them and energy is transferred from one object to the other, possibly even enhancing their vibrations. For example, if you are standing on a bridge, and if the bridge vibrates at the same frequency as your footsteps, the bridge will begin to vibrate more and more vigorously, and this phenomenon is resonance. Sometimes we say that the emotions of a person or a group of people resonate for the same reason. Imagine being with a friend and your emotions and thoughts begin to synchronize, as if you are vibrating on the same frequency. This phenomenon is often seen in collective consciousness, group behavior, and group movements. For example, when a concert or speech begins, the audience on stage resonates with the performer's emotional swings, creating a strong emotional response. This resonance phenomenon illustrates that human beings are not just made up of a single substance, but that we are constantly interacting with the energy fields around us, creating a collective vibration. Interestingly, the law of vibration is not limited to the physical world. It has also been applied to psychology and health. Modern science has discovered that our emotions, thoughts, and even our physical health are all closely related to our internal, vibrational frequency. Have you ever noticed that when you are upset, anxious, or sick, your physical and mental state feels heavy and low? It's as if your energy frequency becomes low, affecting your surroundings and your interactions with others. When you are in a state of joy, peace, and love, your physical and mental, vibrational frequency tends to be at a higher frequency. This high-frequency vibration can help you keep your body healthy, strengthen your immune system, and improve your emotional and mental state. For example, many meditation and yoga practices emphasize the importance of adjusting breathing, posture, and thoughts to change the internal vibrational frequency, thereby achieving balance and harmony between the body and mind. In fact, there is also some research in modern medicine that suggests that certain frequencies of sound or vibration can help restore health to the body. For example, sonic therapy is a method that utilizes sound waves of specific frequencies to treat illnesses. Scientists have found that certain frequencies of sound can help relieve stress, reduce pain, and even promote cellular repair. Some studies have even shown that music therapy has been shown to be effective in treating psychological disorders such as depression and anxiety. On a deeper level, the laws of vibration are also closely related to our perception of the universe and even the nature of consciousness. Have you ever heard the term psychic resonance? Some philosophers and psychologists believe that the universe is not only made of matter and energy, but that it also contains a certain frequency of consciousness. In other words, each of our consciousnesses is constantly vibrating, and our thoughts, feelings, and desires affect the world around us. For example, the famous quantum physicist John Wheeler proposed the theory of a participatory universe, which suggests that we are not just passive beings observing the universe, but that each of our consciousnesses is actually involved in the formation of the universe. In a sense, the vibrational frequency of our thoughts and consciousness may affect the structure and change of the material world. You can think of it as a kind of resonance of consciousness, and our interaction with the universe is actually based on the vibration of one frequency. 2. Symmetry and breaking. First of all, what is symmetry? Symmetry is the property of an object or phenomenon to remain unchanged under certain changes. You can think of it as the concept of mirror reflection. For example, when you look at yourself in front of a mirror, if you stand still, you will look the same in the mirror, right? This is a manifestation of symmetry. The law of symmetry has an extremely important place in physics. In its earliest days, it was reflected in classical mechanics, where Newton's laws themselves contain symmetry in space and time. That is, if you conduct an experiment in one place, the results should be consistent with what they would be if you switched to another place, and the flow of time is not dependent on a particular moment in time. This symmetry of space and time has helped us understand many of the laws of the universe. Why is symmetry so important? Symmetry is not just an aesthetic feature of the universe, it profoundly affects the physical laws of the universe. Scientists even believe that symmetry is one of the foundations of our ability to understand the natural world. For most of the laws of nature, the reason they work so stably is that they follow some kind of symmetry. For example, the Standard Model in physics is a framework for describing particles and their interactions. In this model, the four fundamental forces, gravity, electromagnetism, the strong force, and the weak force, all have their deep symmetries. That is, the way particles interact with each other is not only regular, but will also show certain similar properties because of the symmetry. Since symmetry is so important, what does symmetry breaking mean? Simply put, symmetry breaking means that although many physical processes in the universe follow symmetry, There are some situations that break the balance and cause the system to no longer have its original symmetry. You can think of it as a deviation from the rules. If you do a math problem and derive the answer according to the laws of symmetry, but it turns out that some of the solutions cause asymmetry, this is a sign of symmetry breaking. In nature, symmetry breaking means that some seemingly symmetrical phenomena actually produce asymmetrical results under certain conditions. For example, physicists have found that the initial state of the universe is completely symmetric. That is to say, at the beginning of the birth of the universe, all the fundamental particles and forces are completely symmetric in space and time. But as the universe expanded and cooled, certain symmetries began to break. Such symmetry breaking provides the possibility of diversity and complexity of matter. For example, the original symmetry of particles and antiparticles in the universe evolved through certain physical processes, eventually leading to matter dominating the structure of the universe, while antimatter almost disappeared. You may be wondering, how does symmetry breaking work in practice? Here we have to mention a discovery that rocked the scientific world, the Higgs mechanism. Let's start with the most basic particles. The fundamental particles in particle physics, such as electrons, protons, and photons, interact with each other through some mechanism according to the Standard Model. And behind this mechanism lies a process of symmetry breaking. This process is controlled by the Higgs field. In the 1960s, British physicist Peter Higgs put forward a very unique idea. The universe is filled with something called the Higgs field, which interacts with other particles. As particles travel through this field, their mass is imparted. Originally, the interaction between particles was symmetrical, but because of the Higgs field, the interaction of particles with this field breaks the symmetry and creates mass. In short, the Higgs field is like an ocean, and particles are like fish swimming in the ocean. It is through their interaction with the ocean that particles acquire their mass. Without the Higgs field, particles would not gain mass, and everything in the universe would be very different. Behind this phenomenon is a classic process of symmetry breaking. In 2012, the discovery of the Higgs boson proved the existence of the Higgs field. Scientists have successfully observed traces of this particle in the Large Hadron Collider, LHC, a discovery that provides strong support for the Standard Model in particle physics and gives us a deeper understanding of symmetry breaking. The concept of symmetry breaking is not limited to particle physics. It has far-reaching implications at the macroscopic level of the universe. The universe was initially a state full of symmetry and homogeneity, but as time passed, the temperature dropped, the energy distribution changed, and the symmetry between the various forces began to break, leading to the gradual formation of the structure of matter in the universe. For example, in the very early period after the Big Bang, all the forces of the universe, including gravity, electromagnetism, the strong force and the weak force, were uniform. However, as the universe expanded and cooled, the strong and electromagnetic forces separated, and the weak and strong forces gradually became different. In other words, the fundamental forces of the universe underwent a process of symmetry breaking, and this breaking eventually led to the complex structure of the universe that we see today. In addition, symmetry breaking plays an important role in the phase transitions of matter. For example, the process by which water changes from liquid to ice is a phase transition. At low temperatures, the motion between water molecules slows down, and the symmetry breaking between them causes the water molecules to arrange themselves into the structure of ice crystals, producing solid ice. This phase change is driven by symmetry breaking. The mysteries of symmetry and breaking don't just affect particle physics and cosmology, they are also relevant to our everyday lives. Symmetry has a role to play in art, architecture, music, and even in human thought systems. It is almost universal that symmetry occupies a central place in visual art and architecture. Whether ancient or modern, from the East to the West, aesthetic standards in different cultures often place a high value on symmetry. In civilizations such as ancient Egypt, ancient Greece, and ancient Rome, architectural design was almost always based on strict principles of symmetry. The temples, palaces, and public buildings of these civilizations were often perfectly symmetrical, conveying a sense of sanctity, stability, and harmony. For example, the Parthenon in ancient Greece is a typical symmetrical building that was designed to follow the principle of symmetry perfectly, with every detail striving for perfect symmetry, whether it be from the central columns to the facade on either side. Symmetry here is not only an aesthetic pursuit, it also symbolizes divine perfection and order. Entering the Middle Ages and Renaissance, European churches and buildings were similarly designed on the basis of symmetry. Gothic architecture emphasized vertical lines and symmetrical geometric forms, presenting a sense of pointing to the heavens and reflecting the sacredness and transcendence of religion. During the Renaissance, architects such as Brunelleschi and Michelangelo took symmetry a step further and applied it to grand architectural spaces to achieve visual balance and harmony. Symmetry is also an important element of architectural and garden design in Eastern civilizations such as China, Japan, and India. Ancient Chinese royal buildings, such as the Forbidden City and the planning of Chang'an City, demonstrate a high degree of symmetry in their design. Symmetry is not only visually balanced, but also implies the laws of the universe and nature, conveying the harmony and order between heaven and earth. Japanese garden design emphasizes the harmonious symbiosis of nature and artifice. Although traditional Japanese gardens are dominated by asymmetrical natural landscapes, they still follow a certain deep symmetry, especially in the layout of ponds, bridges, and stone lanterns, which reflects the aesthetics of combining motion and static. In modern architecture, despite the emergence of more free design styles, symmetry still plays a role that cannot be ignored. For example, many famous skyscrapers, museums, public buildings, etc. still use symmetrical design, conveying a stable and harmonious visual effect. For example, the symmetrical layout of the Arc de Triomphe in Paris with its huge doorway is not only a monumental design, it also represents the history and glory of France. So why do humans favor symmetry so much? It's not just a cultural or artistic choice. There are deep psychological and biological reasons behind it. From a biological perspective, symmetry is often linked to health, genetic quality, and adaptability. Studies have shown that humans and other animals often favor symmetrical faces or physical features. This preference is linked to evolutionary psychology. Symmetrical faces and bodies are often considered to be an indication of health and strong genes, suggesting that the person or animal has a high reproductive capacity. In studies of facial symmetry, scientists have found that people with symmetrical faces are usually more popular in society and more likely to find a mate. This tendency is prevalent across cultures and historical periods. Symmetry is seen as a signal that an organism's genes have not suffered too many mutations or diseases, and are therefore more attractive. Symmetry also influences human visual and cognitive preferences. Our brains are able to process and understand symmetrical shapes more efficiently when they are processed. Symmetrical images often give a sense of comfort and balance, whereas asymmetrical images can be unsettling or confusing. In fact, many artists and designers deliberately use symmetry in their work to make it more attractive and acceptable. Even modern artists who seek to innovate and break new ground often use symmetry to increase the visual impact or emotional expression of their work. Symmetry not only appeals to us visually, it also involves deeper cultural and philosophical symbolism. In many civilizations, symmetry represents order, sanctity, and cosmic harmony. Ancient Greek philosophers have long recognized the importance of symmetry and linked it to the order of the universe, mathematics, and philosophical thought. Pythagoras believed that mathematics and symmetry were the keys to understanding the mysteries of the universe. They believed that the harmonious order in the universe could be described by mathematical formulas and that these formulas and structures were inherently symmetrical. The famous golden ratio, 1 minute and 1.618 seconds, is based on this principle of symmetry, and it is still widely used today in architecture, art, and nature. In many religious traditions, symmetry is viewed as a sacred symbol. In religions such as Christianity, Islam, and Buddhism, buildings and motifs often employ symmetry to express the infinity of God and the order of the universe. Islamic mosques, for example, often include beautiful geometric symmetrical patterns in their designs, which are believed to symbolize God's infinity and symmetrical divine order. In Buddhist temple architecture, symmetry is often used to express philosophical ideas such as emptiness and existence, egolessness and impermanence, reflecting the harmony and change of the universe. The mandala motifs of Buddhism, as well as the ancient temple architecture of India, are based on a strict symmetry design, symbolizing the purification and transcendence of the soul. Symmetry occupies a pivotal position in the field of science, especially in physics. Scientists believe that the most fundamental natural and material laws of the universe often exhibit some form of symmetry. In modern physics, especially particle physics and cosmology, symmetry and symmetry breaking are key to understanding nature. The Standard Model describes elementary particles and the interactions between them, and one of the centers of this model is symmetry. The interactions between particles follow certain symmetry principles. The Higgs mechanism and symmetry breaking in particle physics are key to understanding the origin of mass and force. On a more macroscopic level, cosmology also relies on symmetry principles. One of the assumptions of the Big Bang Theory is that the initial state of the universe was perfectly symmetrical, and that over time, the matter and energy in the universe began to form the complex structures it has today through symmetry breaking. Scientists have gradually revealed the evolution of the universe by studying its symmetries. There are many important theories in mathematics that are closely related to symmetry. For example, group theory is the branch of mathematics that studies symmetry, and it is widely used in physics, chemistry, and even music. Through the study of symmetry groups, scientists are able to understand the behavior of particles and fluctuations more clearly, and even reveal deep laws hidden in nature. The concepts of symmetry and breaking may seem abstract, but they can be found in every corner of the universe. From particle physics to cosmology, from the origin of life to human culture, we feel their existence all the time. 3. Scale invariance. Scale invariance. Scale invariance, the name may sound a bit complicated, but to put it plainly, it refers to the fact that the behavior of a system or phenomenon is similar at different scales. From an everyday perspective, scale invariance is a bit like self-similarity in that you can see repeating structures. Whether you're looking at the branches of a tree or zooming in on the details of each leaf, you'll find a similar pattern. Scale invariance plays an important role in cosmology, physics, and even in the life sciences. It tells us that many complex systems exhibit similar behavior at different scales, and it seems that the universe itself follows some kind of self-replicating rules at different levels. We can understand scale invariance from some more intuitive examples. First, think of fractal patterns in nature. You've seen similar patterns, snowflakes, tree branches, river branches, etc., and no matter how far away you look, zoom in or zoom out, you can see a similar structure. In simple terms, it means that when you zoom in on a certain part, you still see a repeating pattern throughout the structure. In more academic terms, scale invariance refers to the fact that certain laws of physics, phenomena, or system behavior remain constant at different scales. This invariance makes the overall behavior of the system scale-independent. For example, certain properties of an object such as shape, structure, or even behavior may not change when you zoom in or out of an object, which is a manifestation of scale invariance. Fractals are the most representative mathematical tool for studying scale invariance. In the early 20th century, mathematician Benno Mandelbrot introduced the concept of fractals and showed how many phenomena in nature can be described through fractal geometry. One of the central properties of fractals is their self-similarity. No matter how many times you zoom in, you will always see similar structures. Let's take the Mandelbrot set as an example of a typical fractal pattern. You might see it from a distance and it might appear to have a simple outline, but if you look at it with a higher magnification, you'll see that every part of the pattern almost reproduces the original figure on a smaller scale. It's like a microcosm of the universe. Whether you look at the distribution of galaxies on a large scale or at the behavior of electrons on a microscopic scale, there is a certain similarity to be found. In nature, many phenomena exhibit fractal features. For example, the vascular system, the branches of a tree, and the contours of a coastline all exhibit some kind of self-similar structure at different scales. Such fractal patterns are not only found in physical phenomena in nature, but even inside our bodies, there are many fractal structures. For example, the structure of the human lungs is like a complex fractal. Each time we inhale air, it flows along smaller and smaller bronchial tubes and ends up in tiny alveoli. This pattern of branching, which behaves similarly at different scales, creates a classic scale invariance. You can look at the details of the alveoli at the microscopic level, or you can look at the entire bronchial system at the macroscopic level, and you will find similar branching structures. Scale invariance is not just a mathematical and geometrical concept, it occupies a very important place in physics as well. In fact, some of the most fundamental laws and theories of modern physics embody scale invariance. Let us look at a few concrete examples. In quantum physics, scale invariance is an important way to describe particle interactions. Quantum field theory is one of the major theories of modern physics, which tells us that every particle in the universe is described by some kind of field, and that the behavior of these fields is similar at different scales. In high-energy physics, symmetry and scale invariance are often closely related. For example, in the case of certain particle interactions, the behavior of the particles and the mode of interaction change with increasing energy, but they follow some form of invariance law. In fact, the tool of the reification group is used to study exactly how the laws of physics remain consistent at different scales. With this mathematical tool, physicists are able to derive phenomena at the macroscopic scale from the microscopic scale. The successful application of reorganization groups has helped physicists gain a deeper understanding of areas such as quantum field theory, statistical physics, and even provided us with clues about the early state of the universe. General relativity is one of the most successful theories for describing gravity. In this theoretical framework, space and time are not fixed, but can be bent by the distribution of matter and energy. However, the laws of this bending are scale invariant at different scales. That is, from small-scale atoms to large-scale galaxies, the gravitational behavior of the universe follows similar laws at different scales. In addition, scientists studying the origin of the universe have found that the universe appeared to be scale invariant for all physical laws and phenomena in the very early days after the Big Bang. At that time, the universe was extremely hot and dense, and the behavior of particles and energy showed similar patterns for very short periods of time and at very high energies. As the universe expanded and cooled, scale invariance gradually broke down, and the laws of physics began to exhibit scale-dependent behavior. This early state of the universe is often referred to by physicists as the realm of quantum gravity. A critical phenomenon is a phase transition in a physical system in which the properties of the system change abruptly near a critical point. For example, the change of water from a liquid to a gas, or the change from a ferromagnetic state to a non-magnetic state of a magnetic material, are all phase transition phenomena. Near the critical point, the system exhibits scale invariance. That is, no matter how much you zoom in or out of the system, the behavior and properties of the system will exhibit a self-similarity near the critical point. This is particularly important in statistical physics. Physicists use critical exponents to describe how various properties of matter change with time or temperature near a critical point. The similarity in the behavior of different substances near a critical point reflects the universality of scale invariance. Scale invariance occupies a very important place in the structure of the universe. Through the concept of scale invariance, we can understand the laws of formation and distribution of the large-scale structures of the universe and how they maintain similar forms and patterns, both on very large and very small scales. The large-scale structure of the universe, as the name suggests, refers to the large-scale distribution patterns of matter, e.g., galaxies, star clusters, dark matter, and gas in the universe. The grid of the universe as we know it is the structure that presents itself on very large scales. This grid consists of galaxies, clusters of galaxies, and larger structures, such as superclusters of galaxies, that are connected to each other and form a spiderweb-like pattern. These structures are not uniformly distributed, but show a regular distribution pattern. From our observations, the structure of the universe appears to be unevenly distributed, with galaxies and galaxy clusters separated from each other by vast regions of voids and voids. The distribution of these galaxies and clusters of galaxies forms a vast, web-like structure that scientists call the cosmic web. This mesh is characterized by a similar distribution pattern no matter what scale you look at. Scale invariance means that no matter what part of the universe we're looking at, whether it's 1,000 light-years, 1,000,000 light-years, or 10 billion light-years, the distribution of matter in the universe exhibits a self-similarity and regularity. That is, galaxies, clusters of galaxies, voids, and other structures exhibit similar morphology at different scales. For example, the relationship between the void part of the distribution and the clusters of galaxies maintains a certain symmetry or regularity at each scale. This regularity is a manifestation of scale invariance. To understand this more intuitively, we can make an analogy with fractal geometry. A fractal is a self-similar structure, which usually exhibits similar forms at different scales. The vast structure of the universe is a giant, fractal, and each of its parts may exhibit similar organization at different scales. Through modern telescopes and deep sky surveys, astronomers have discovered that the cosmic grid exhibits a fractal character on large scales, a uniform pattern of structure from the tiny voids at the beginning to the huge groups of galaxies. In the 1980s, astronomers began to image the large-scale structure of the universe using large-scale redshift surveys such as 2DF and SDSS. Through these observations, scientists discovered that the distribution of matter in the universe is not random, but shows a certain regularity. In particular, by studying the positions and motions of millions of galaxies, scientists revealed that these galaxies are not uniformly distributed, but form a structure similar to a mesh. The formation of this structure can be traced back to the beginning of the universe. At that time, the matter in the universe was not evenly distributed, but gradually gathered into large-scale structures through some kind of tiny fluctuations. As the universe expanded and the matter gravitationally gathered, galaxies, clusters of galaxies, and larger structures were formed. And these structures, on both large and small scales, maintain a similar pattern. Fractal structure and scale invariance are inseparable in the formation of the cosmic grid. Physicists have found that the distribution of the universe exhibits a fractal-like structure on large scales. For example, astronomers analyzing clusters of galaxies have found that on scales of hundreds of millions of light-years or thousands of light-years, we can see a similar structure, a group of clusters of galaxies on one scale, and many clusters of galaxies on another scale, forming a larger structure. The appearance of such self-similar structures is a reflection of scale invariance. In other words, the pattern of the distribution of matter in the universe remains consistent at all scales, and the repetition of this pattern reflects the intrinsic law of the evolution of the universe. According to existing theories, about 13.8 billion years ago, the universe began to explode and expand from an extremely dense and hot state. The early universe was not a homogeneous space, but was filled with tiny fluctuations. These fluctuations existed in the early universe in the form of quantum ups and downs, which were very tiny and imperceptible, but provided the basis for the formation of the large-scale structure of the universe later. These quantum ups and downs, although extremely tiny on the scale of the early universe, are scale invariant. They produce similar fluctuations at different scales. As the universe expanded, these fluctuations were amplified on different spatial scales, eventually forming the structure of galaxies and galaxy clusters that we see today. These initial fluctuations actually maintain their properties through the principle of scale invariance, gradually evolving throughout the evolution of the universe into the cosmic web we see today. Bulge theory further explains the important role of scale invariance in the early universe. According to the inflation theory, in the very short time after the Big Bang, the universe underwent an extremely rapid expansion. This expansion was so fast that the universe expanded several times in a very short time. During the inflationary process, the change in scale of the universe is scale invariant, i.e., the universe expands at a uniform rate, and this expansion is similar for any region of space. The theory of bulge inflation proposes that during this process, all regions of the universe experience similar quantum ups and downs and were amplified equally during the expansion process, creating the grid structure of the universe that we see today. This is why the distribution of matter in the universe is characterized by self-similarity. During the inflationary period, the scale invariance was not only reflected in the expansion of space, but also in the distribution of energy and matter, so that the structure of today's universe shows similar patterns on all scales. Scale invariance not only affects the past and present of the universe, it may also have far-reaching implications for the future of the universe. Scientists believe that the structure of the universe may continue to maintain some scale invariance, especially during the evolution of large-scale structures. As the universe continues to expand, the distances between galaxies will increase, and the overall structure of the universe may become more sparse. Well, that's it for this installment. Feel free to like and comment. Thanks for watching.